Hi, the last part of the lab report document is just a review, the VSEPR shape name and the resonance. Remember that VSEPR stands for valence shell electron pair repulsion. The important thing is to use the table from page 118 of your textbook. I had a slide like this in the lecture 1.5 weeks ago, but I added a shape called Trigonal Planar. I suggest you write this information down, maybe in your book, or if you print a page like this from the internet. I mean, the internet is full of tables like this. Make sure that it has trigonal planar there. Let me show you how to use this to find the VSEPR shape. My molecule is going to be the nitrite ion. Nitrite ion. First, I got to draw the Lewis structure. Put the first atom in the middle, put the other atoms around it, hook them up like that, give the negative charge. This is -1, so I'm going to put -1 outside the brackets to make sure that we all know this is negative. Why is that important? It's important because when you count the valence electrons, this is 5 valence electrons from the periodic table. This one has 6 valence electrons, but there are 2 of them, so we get 12. And there's that extra negative charge. That means an extra electron. So add them all up. You get 18. There are 18 electrons here. I'm going to let everybody follow the octet rule and then see what happens. Let's count them. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. I have 20 electrons here. Is that a correct structure? No. It's supposed to have 18. So I'll make a little double bond, and of course, when you make a double bond, you have to erase some lone pairs because they're being shared. The electrons are being shared now. You don't get your own. You don't get your own. You need to share. Okay. So now let's count again. 2, 4, 6, 8, 10, 12, 14, 16, 18. Great. Now this is 18 valence electrons, and that is correct. Is everyone still following the octet rule? 2, 4, 6, 8? Yes. 2, 4, 6, 8? Yes. 2, 4, 6, 8? Yes. We're all following the octet rule. Now, this shape looks linear. You see? They all line up. So is the shape linear? No, of course not. You need to use the table here. So let's see. Number of bonded atoms to the central atom. Well, this is an atom bonded to the central atom. And this is an atom bonded to the central atom. So there are 2 atoms bonded to the central atom. There are 2. So there are 2 atoms bonded to the central atom. Okay, so it's either this shape linear or this shape bent. Right now, number of non-bonded electron pairs on central atom. You see there is this electron pair. It is non-bonded. It is on the central atom. So there is a non-bond. So it can't be linear because this is 0. This has no non-bonded electron pairs on the central atom. The bent shape has 2 non-bonded electron pairs on the central atom. This molecule only has 1. I'm going to change this table to say 1 or 2. And the reason is it can't be linear because this electron pair takes up space. It takes up more space than a chemical bond. So these bonds are going to be bent like this. Okay? So it's not going to be quite as bent as the water molecule. The angle here, this angle here, is something like 108 degrees on the water molecule, or 105 degrees, or something less than 120. The angle here is going to be maybe 112 degrees, or something almost 120. The difference is because this one has 2 lone pairs. This one only has 1 lone pair. But we'll still call this bent. Okay? So the molecular shape will be bent. I'll give you a hint right now. I believe there is another molecule on your lab report document that is bent in this way. It has only 1 lone pair on the central atom. Yes, I'm pretty sure that there's got to be at least one molecule on here that has only one lone pair on the central atom, and you're going to call it bent. So you should make a note somewhere that bent is going to mean two atoms bonded to the central atom and one or two lone pairs on the central atom. Okay? That is how to use this table. Now, that means, let's see, where would you write that word bent? You would write it right here. You would write bent right there. If this were the nitrite ion, you would write bent right there. That's how to use that table. Now, because trigonal planar is something that's not in your book, and it's something that I added during the lecture, I want to review it for you one more time right here. Suppose you have this molecule, CH2O. This is formaldehyde. And you draw the Lewis structure like this. It has three atoms bonded to the central atom. There's this hydrogen, and this oxygen. They are all bonded to the central atom. Now, this atom in the middle, carbon, it has no lone pairs. So that it has 0 lone pairs. So it has 3 atoms bonded to it, 1, 2, 3, but 0 lone pairs. That means it's trigonal planar. So it looks like this. When you make this as a toy, it is flat. If you rotate this, you will see it is flat. So that's how you identify something that is trigonal planar. I believe that there is something that is trigonal planar on the lab report document. I'm not sure, but I kind of believe that there would be such a thing. It might not be. Now, the last thing is resonance. I need to review for you the resonance. So this molecule here, does this molecule have resonance? No. Why not? Because, I mean, ordinarily you might draw resonance like this, right? Oops, sorry. There is a double bond, so you might decide to draw resonance like this, right? Just move that double bond around to everybody, right? Little brackets to show that it's resonance. But this would be wrong, because remember, hydrogen is too small. It can only have 2 electrons. It can only make 1 bond, not a double bond. So this is impossible. You cannot have anything more than 1 bond on the hydrogen. In this case of resonance, this would be a 1.33 bond, a 1 1/3 bond. This would be 1 1/3 bond, but it is impossible. Hydrogen is too small. Where can you see resonance then? If you have a double bond, then you might be able to see resonance if there are other atoms that are not hydrogen. Let me show you what I mean. I just did the nitrite ion in the previous example, right? I drew the Lewis structure something like this. Now that I know that it is bent, I'm just going to draw it as bent. But you see, this is a single bond and this is a double bond. This is an O and this is an O. It is not important that this is O. It is just important that this atom is the same as this atom. If you have this atom, the same as this atom, and there's one of them that has a single bond to the center and the other has a double bond to the center, well, switch that. This is how you determine resonance. Okay, is this a correct Lewis structure? Yes. Is this a correct Lewis structure? Yes. Then there is resonance. This is the resonance structure. You do not need to draw the resonance structure. You just need to say yes. Where do you say yes? You say yes right here. Yes, like that. Right? Remember, again, resonance does not mean that the molecule has 2 forms. Resonance means that this is not a single bond. This is not a double bond. This is something in between a single bond and a double bond. So this is a 1.5 bond. This is also a 1.5 bond, right? We just don't draw these dotted lines because they're confusing. All right. And that is, oh, did I, you don't put yeah, you put yes. Okay. I think that is all. Thank you.